This video is about vectors and their relationship with some other things, including suspension problems. So the difference between a vector and a scalar is something that's important to note. A scalar is just something that has a magnitude, but a vector has magnitude and direction. So if you look at all of these things that are scalars, time, distance, mass, area, and so on, all of these things are just numerical values. Whereas all of these things that are vectors, like displacement, there's a value that's associated with not just the magnitude, but also which way you're going. So you can have negative displacement, whereas distance is always just a numerical value. And so all of these things are vectors in some way because they have a magnitude and a direction. So if we look at these problems, a car is traveling 50 miles an hour. That is a scalar. Whereas if it's traveling 50 miles an hour and it's due north, then we say it is a vector. So scalar and vector. Football players running 5 miles an hour toward the end zone would be a vector. But the volume of a box is a scalar. Even though we tell you where it is in the building, that's not really relevant for what's happening. We're going to add some vectors now. So what we have is the vector 1, 2 and the vector 3, 3. If we add them, we get 4, 5. And how we can actually add these two is we can take one of the vectors, put it at the edge of the other vector, and then just add that vector to it. And then what we see is the resultant vector is 4, 5. We can do the same thing over here. So this vector we know should end up being 3, negative 1. If I take this vector 4, 1 and go 1, 2, 3, 4, 1, notice that my resultant vector from the origin would be 3, negative 1. It does not matter which vector I start with. So if I use this colored one and I go negative 1, negative 2, notice that I still end up with the vector 3, negative 1. Write a unit vector in component form. So that's the A, B with the pointy brackets. If the initial point is 2, 6 and the terminal point is negative 4, 9. So we already did this, but we'll practice it again. Step 1, we're going to find the vector. So the vector here, if you can't see it, the arrow is over here. But we're going to find the vector P1, P2. So we will subtract these two things from each other, and we will get negative 6, 3. So that's this vector. Then we find the length of this vector, which is the square root of 6 squared plus 3 squared, which is the square root of 45. You can simplify that, but it's not necessary. And then to get this unit vector, which we'll call u, we take the square root of 45 and divide each of the parts. And that's our answer. Number 4, write a vector in the AI plus BJ form, given that its magnitude is 6 units and it makes a 60-degree angle with the positive x-axis. So here's our answer. And how we get there is we can take a drawing where we have something that looks like a 60-degree angle. The magnitude is 6 units, and we want to convert this to figure out what is going in the x direction and what's going in the y direction. So if we find out what's going in the x direction and what's going in the y direction, then we could just find the whole magnitude of this thing. So I can use the cosine and the sine, or I can just know what the cosine and sine of 60 degrees are, and then I don't have to write this actually all the way out. So the cosine of 60 is 1/2, so I just take 1/2 of 6 and I get 3. That is my I component, and then my j component is 3 root 3. So if I wanted to write it in component form, I would say 3 comma 3 root 3, but my answer has to be written in i's and j's because that's what it says, so that's what I write. Now I'm going to write a vector whose magnitude is root 20, and component in the negative I direction is 4 times that of the component in the positive j direction. So the first thing I'm going to do is I'm going to call this unknown length a of some kind. And so in the positive j direction, I'm going to go a, but in the negative I direction, I'm going to go 4 times a. So a is just my unknown quantity that I'm going to have to plug back in to see what the answer is. Now, I know that the magnitude of this vector v is the square root of 20. And I also know that the magnitude is going to be the I part squared plus the j part squared. So I have 16a squared plus a squared inside of a square root. So the square root of 17a squared is equal to the square root of 20. Then you just do a little solving and you end up getting the square root of 20/17. You do not have to simplify that in this unit. You can just leave it like that. Now let's talk about force. From the last activity, or yesterday, we recall that force vectors are written as the magnitude of the force times the cosine of theta in the I direction plus the sine of theta in the j direction. That's because cosine goes with the x-axis and sine goes with the y-axis, which is something that we already know from Algebra 2 and every other time we've used trig. So now a force of 30 newtons, so that's our magnitude of the force, acts on an object with an angle of 45 degrees with the positive x-axis. A second force of 40 newtons acts on the same object at an angle of 60 degrees or negative 60 degrees with the positive x-axis. So basically what we have pictorially is something that looks like this. We have a 45-degree angle going this way, and we have a 60-degree angle going downward this way. Now, when we add forces, it's just like when we added vectors here. We can just take one of the forces and put it at the end of the other force. So when I do this, what I end up doing is I just take this first force of 30 newtons, the second force of 40 newtons, and I add them together, and then this ends up being the picture of what my resulting force is. So we want to find the direction and magnitude of this resulting force. And so what I can do is I can figure out that the first force, which I will call F1, is the magnitude of F1 times cosine of 45 plus, or I, plus sine of 45j. And likewise for force 2, it's a 40-degree Newton force, or 40 Newton force going down 60. So I can take these two forces and then I can write them either in i's and j's or in component form. I'm going to take component form. So this one's going to be 15 root 2, 15 root 2. And notice that I probably should know the cosine and sine of these things, and I probably don't have to write it if I have an awareness of what the sine and cosine of our major angles are. But if we end up getting some nastier angles, then you're probably going to have to use a calculator or write this stuff out. Now, when I'm dealing with the cosine and sine of negative 60, I'm going to end up with 20 and negative 20 root 3. So then I just add these two forces together. And I end up with this answer. So the resulting force is what happens when I add these two things together. So that is 15 root 2 plus 20, comma, 15 root 2 minus 20 root 3. Then in the calculator, you can get approximations for this. So that's 41.213, negative 13.428. So that gives me the force, and then the magnitude and the direction. What I can do is I can plug these two numbers into the Pythagorean theorem, and I get this number. And then if I want to get the direction, I do the arctan of y over x, or the j component and the I component, and then I end up with this in terms of radians, or I can get it in terms of degrees if I want, by multiplying by 180 and dividing by pi. Now, an object is said to be in static equilibrium if it's at rest and the sum of all forces acting on the object is 0. In other words, the resultant force is equal to 0. So in this problem, the resultant force was non-zero, right? Something started somewhere and ended somewhere else. So this was what actually happened to the object. If we have static equilibrium, the object is not going anywhere. So let's take a look at this problem. We have a box that's 500 pounds, or a suspended weight that's 500 pounds, and it's not moving. So we want to find the tension of the forces in the cables. So what we would do is we have this force diagram. So the force being pulled down on the box is gravity. It's really not that hard to just realize that that is 0, negative 500. You don't need to do all the things with the cosines here, because you should know what that is. It's all in the y direction. But if you want to, that's fine. So now we have these other forces, F1 and F2, and if I pull them out, I have X, which is an unknown magnitude, times cosine and sine of 45, and then Y times cosine and sine of 150 in this vector. And that's because the cosine and sine are of this 150 degree angle. So if you want to do this, you also, like, sometimes I write this one in a slightly different way. So what I also do on occasion is I might write y times negative cosine of 30 positive sine of 30, just because I know that this 30 degree angle is pulling me where x is negative and y is positive. So it's going to do the same thing, because what happens when you have cosine of 150? You end up with a negative number. So either way is fine. So now what you want to do, since this object is at equilibrium, you have force 1 is root 2 over 2x, root 2 over 2x. Force 2 is root 3 over 2y, negative, and then 1/2 y, and then this is force 3. What do we do with all these things? We have to make sure that all of these forces add up to 0. So we know that because the object is in static equilibrium. So what we can do is we can take all of these things, all of these x's, add them up and set them equal to 0. We can take all of these y's, add them up and set them equal to 0. So we have these two things that are happening. So this is all my x components, and this is all my y components. And if I add up all the forces, it has to equal 0. So I end up with these two situations, and now I have a system of equations. So now what you do is you can either solve the system by hand, which I don't recommend, or you can type it into the calculator using a matrix like you learned in Algebra 2, and then you end up getting these values. So the force, the magnitude of the force in string 1 or rope 1 or cable 1 is 448.288, and the magnitude of force 2 is 366.025. I recommend you do number 2 on your own, and the answers are these two numbers. They're actually pretty similar to each other, but this problem is very much like the first suspension problem. So I recommend that you do this on your own and see if you get these answers.